Recall that to find the eigenvalues of a matrix, we solve a polynomial equation. And polynomial equations can have repeated roots, solutions that come up more than once. Let's see what happens to the eigenvectors in those cases. So first of all, recall that for a fixed lambda, some real number, the eigenvectors are solutions of A minus lambda I. So the solutions V of A minus lambda I V equals 0. And all such solutions form a space, the null space of A minus lambda I. Now this consists of all eigenvectors having eigenvalue lambda. So let's call this the lambda eigenspace of A. Now, if a solution, let's say lambda equals C, to the characteristic equation determinant A minus lambda I equals 0, if that solution appears with multiplicity k, does the C eigenspace have dimension k? That is a basis of k linearly independent eigenvectors. And oops, I'm running out of space. The answer is no, not necessarily. So if lambda equals C appears with multiplicity k, then that C eigenspace is going to have dimension somewhere between 1 and k, but not necessarily k. So let's look at an example. Let's look at two different examples where we get different dimensions for the same multiplicity of a certain eigenvalue. So for example, let's let A be the matrix that has 2, 2, 1 on the diagonal, and then 1 right here and zeros everywhere else. The determinant of A minus lambda I equals determinant of 2 minus lambda 0, 0, 0, 2 minus lambda, 1, 0, 0, 1 minus lambda. This is an upper triangular matrix, so the determinant is just the product of the diagonal entries. So that's 2 minus lambda squared, 1 minus lambda. So lambda equals 2, we say, is a solution with multiplicity 2 because of this squared factor. All right, then we'll solve a minus 2i v equals 0 to find eigenvectors. So that is a is right here, a minus 2i is going to be, we'll take 2 off of the diagonal entries, 0, 0, negative 1 on the diagonal, and leave everything else exactly as it is. Oh, I went off the space again. I will put that above. So we take 2 off of the diagonal entries and get 0, 0, negative 1 on the diagonal. Copy the other entries. So we solve this, and I guess v3 equals 0. And then without the v3, we just have 0 v1 plus 0 v2 equals 0. So v1 and v2 could be anything. So we could say v1 equals s, v2 equals t. So the 2 eigenspace is all the vectors s, t, 0, where s and t are real. So this is two-dimensional. One basis is 1, 0, 0, 0, 1, 0. Now, I just erased the matrix, but we had A equals 2, 0, 0, 0, 2, 1, 0, 0, 1. All right, and if we find the one eigenspace, we'll take 1 off the diagonal, 1, 0, 0, 0, 1, 1, 0, 0, 0, v1, v2, v3 equals 0, 0, 0. Last equation is gone. So the second equation says that v2 plus v3 equals 0. So that means that v2 equals negative v3. And then the first equation says v1 equals 0. So the one eigenspace is, we just need the second and third components to be opposite. So 0t, negative t, as t varies over all real numbers. And one basis is 0, 1, negative 1. So here, if we take the bases of the 2 eigenspace and the basis of the 1 eigenspace, we get a basis for all of our 3. So the 2 eigenspace basis union the 1 eigenspace basis is 1, 0, 0, 0, 1, 0, 0, 1, negative 1. Which forms a basis of R3. Now let's look at a slightly different matrix. I'm going to put one more 1 in this matrix right between the two 2's. So now let's consider A with 1's right above the diagonal in addition to the 2, 2, 1 on the diagonal. So the eigenvalues are still 1 and 2 because this is an upper triangular matrix and the diagonal entries are the eigenvalues. Let's look for the 2 eigenspace. This was 2-dimensional in the last example. So we're going to solve A minus 2i v equals 0 for v. So we'll take 2 off of the diagonal, 0, 0, negative 1, leave everything else the way it is. So that matrix times v1, v2, v3 equals 0, 0, 0. And it looks like v3 equals 0, and v2 equals 0, and the v1 equals anything. So the 2 eigenspace is anything 0, 0. So t can be any real number. That's 1-dimensional. One basis is 1, 0, 0. This is 1-dimensional even though 2 came up with multiplicity 2 in the characteristic equation. Determinants A minus lambda I equals 0. And then if we look at the 1 eigenspace, so we'll take 1 off the diagonal. We'll solve A minus 1i v equals 0. 1, 1, 0. On the diagonal. So this matrix times v1, v2, v3 equals 0, 0, 0. Last equation is nothing. Second equation says v2 plus v3 equals 0. So v2, I guess, equals negative v3. And then the first equation says v1 plus v2 equals 0. So that means that v1 equals negative v2. So v1 is the opposite of v2 and v3 is the opposite of v2. I guess v1 and v3 have to be equal. So the 1 eigenspace is t, negative t, t, where t varies over all real numbers. And one basis, most obvious basis, is 1, negative 1, 1. So the 2 eigenspace basis and the 1 eigenspace basis together make a 2-dimensional space. So 2 eigenspace basis union the 1 eigenspace make a 2-element basis. So 1, negative 1, 1, and 1, 0, 0. Now sometimes the dimensions of the different eigenspaces add up to the dimension of the whole space. But if the dimensions of the eigenspaces of A add up to less than Rn, well, less than n, then we call A defective. So if an eigenvalue comes up k times, maybe we can find a k element basis for the eigenspace, or maybe the eigenspace has dimension less than k. The end.